Okay, I think we're going to get started this morning. Hope everyone survived our little snow here. It'll be interesting to see if this continues in April. One of our snowiest months ever was when we got 50 inches of snow in one April. So I'm hoping we don't see a repeat of that here. At least it should be warmer today and tomorrow, so it should melt for this. I'm just excited because usually we're headed to the mix conference, Allie, on tomorrow, and students are going down to MUDAC competition. And my wife claims that every time I take students to a mixed competition, it is a horrible snowstorm. There, we've driven through Iowa, North Dakota, and Wisconsin through some really bad weather trying to get to programming and robotic competition. So I think the weather gods just got confused and gave us the storm a couple days early. So I think we'll be okay this weekend, tomorrow, when we head down there. So that'll be nice. Good change of pace. So, um, all right. So we're gonna do continue with unit 11 today, Turing machines. We're gonna work more on programming Turing machines this week. And then next week, we're gonna spend some more time on some of the theoretical proofs and stuff. There's this whole idea of diagonalization and halting problem proofs there, and we're going to be looking at those next week. Once we kind of have a better understanding of how Turing machines kind of work. So the goal today is really to get you some experience working with Turing machines and understanding how they work. I mean, they're not that complex of a system, and but I think it has helped to kind of do some problems with them to kind of understand how they work. Also to see how quickly problems are become actually quite hard to do on a Turing machine, and the difference between theory and practice with these stuff. So that's what we're going to be doing today. We're going to start. I'm just going to walk through some of these discussion questions with you. I'm going to turn this around and look at this. And then again, if you are here, either online or stuff, you can participate, but we'll mark you off as being active and getting your discussion points for your replies this way. See if I can get this around. Okay. And let's bring up. Yeah. I've had a good variety of questions the students asking in the discussion this week. I kind of grouped them in practical and then more theoretical and more philosophical. So we're going to start with the practical ones. I think so. One thing I'd ask, like first of all, ask is this: how many different subroutines can you add to Turing machines until they become too big to manage and have to be refactored into something else? Um, One of the things that's interesting in Turing machines is we really don't do that much with them, and we don't write big. We kind of show how we can do things often, but we often don't write any sort of complex software Turing machines because, as you'll see today, they become very complicated very quickly. And although you can do subroutines, we can show how to do subroutines with them. We can also show how you can simulate like multiple tapes on a Turing machine. Even though it has one tape, you can divide it up or set several ways so that it can simulate multiple tapes and stuff like that. But we don't generally refactor stuff in a Turing machine. We don't. I mean, these are more theoretical than practical, I guess. No one does any real work in a Turing machine, I guess. So I don't know if that happens very often. What's your thought on the next one? Are there programming languages that can simulate a universal Turing machine? So you've seen Turing machines. We're going to run a simulation of one today. Can most programming languages simulate a Turing machine? Is there something in a Turing machine that programming that you could program? We have a tape that moves back and forth there. We have some rules. We read an input, write an output to the tape, move either left or right there. So again, most of that stuff can be simulated with any programming language there. Some people would argue that the whole infinite tape sort of thing might be a little problem, that we have an infinite tape there, but in practice, we don't worry about that much. We always think, well, we can always add more memory or storage there, or do something like that for it. So I think most of these things are called. Well, we have this idea of Turing complete, and like almost all modern programming languages are assumed to be Turing complete in that you can simulate a Turing machine, and anything you can do on a Turing machine you can do in Java or JavaScript or Python or stuff like that. So, the next one gets to the heart of these languages, and of course we talk about like Turing recognizable languages. The next couple questions talk about that, and I think it's important to kind of differentiate programming languages from Turing languages. So most of our languages that we handle in Turing with Turing problems are not programming. I mean, the idea in theory is that you could write a Turing machine that could recognize Java and all of Java's syntax and stuff. And that's why we looked at how we can take a language like Java or Python and write it and parse it with like Bacchus-Naur form. We can create rules for what are legal expressions, and so we can kind of define how that whole language works. So certainly you could write Turing machines that could recognize all of Java there, but generally we don't, and often we're working with much more simplified languages. So we'll see languages today. So like we'll just work with binary, like the set of binary numbers, or the set of words that just have the letters A, B, C in them there in different combinations. And then we might put some limitations on that. So we might ask, can we create a Turing machine that like today will do, they'll recognize the language where we'll have a sequence of A's and then followed by a sequence of B's. And then the number of B's will always be equal to the number of A's and things like that. So, when we're talking about languages and Turing machines, often they're simplified languages, often not like Java. I mean, the theory is that we can recognize all languages like Java and stuff like that, but we often aren't. And then how does understanding Turing machines help us design better algorithms and optimize computer processing? I would have to say it doesn't. I mean, this is a theoretical kind of idea and not a practical sort of idea. So don't think, I think it certainly helps you with your way of thinking of things, but I don't think it really helps you solve, write algorithms. You don't like develop an algorithm on a Turing machine and then move it over to Java or something like that. I don't think. You'll have to see today. We'll do some algorithm. We'll do like checking if a word is a palindrome or not, or adding one to a binary number. And you should see today if doing that on a Turing machine, changes the way you think about algorithms and stuff like that. Because I think there could be an argument for that. But to me, it's much more theoretical and philosophical. What Turing machines let us ask, what can we do with computers and what can't we do with computers, not what we will, what practically we do. So, some of the theoretical ones I'm going to wait till next week, I think. Again, we're going to do a couple diagonalization proofs next week, and we'll talk about what proofs are also, and how we set up a proof. We haven't really talked too much about that, so we'll talk about proofs. I don't know, have you done proofs in classes like geometry class, maybe, or calculus class? You've done some proofs at some point, maybe. So we'll talk about some proofs and that, and we'll look at some of the big proofs related. We'll look at the whole class of proofs in these theoretical things for diagonalization. We'll start by proving that the number of integers is not the same. We have an infinite number of integers, but that's not the same size as the number of real numbers. And so there'll be more one than the other. We'll look at some of that stuff. And then we'll take that, once we kind of understand how diagonalization works, we'll try to apply it to Turing machines for that. We will look at this undecidable versus unrecognizable stuff. And so just remember, today we'll write algorithms that will either enter an accept state or a reject state, or they might just loop forever. And so if we have a language that if something's in the language, we'll always get to the accept state, then the machine can recognize it. Anything that's in the language, we can know. But if it's not in the language, we don't know, because we can give it to it and it might loop forever. And sometimes that's hard because you don't know if something is just taking a long time, or if it's we've all run programs where you run the program and and it's sitting there spinning and you're going, is this looping forever, or is this just taking a long time? Like, we're just doing some of this data analysis, and there's 34,000 records in the thing. And so anything that's processing at 34,000 records sometimes is taking a long time. You don't know, but you don't know if is it taking a long time, or is it just looping forever? So that gets to the heart of that sort of stuff. Recognizable. So if it's decidable, then you're guaranteed to either get to an accept state or a reject state. It won't loop forever. So I guess that's decidable, is that one. And again, we'll talk a little bit more about this philosophical concepts. Gets us into this, like someone was asking, if anything is computable, if anything that is computable can be done on a Turing machine, does that mean the brain is really just an advanced, computer there? And again, that's one of the big questions, philosophical questions there is what is, and it gets kind of the heart of intelligence and creativity there, and free will, determinism. If we can just write this as a computer program, that is, those thing gets to do with, we're beginning to see much more. We talk about this a little bit, machine learning, much more realistic, AI, general purpose AI, and I think we'll be seeing much more realistic, robots in the next 10 years. And so, we get into a lot of these science fiction questions about is a robot intelligent or not? And then I think once you start opening up those questions, is simulating intelligence the same thing as being intelligent there? Is simulating the brain the same as having a brain. And then once you start asking that, you ask, well, is simulating emotions the same as having emotions to simulate consciousness, or, the same as being, what does it mean to do those things? You should start thinking about, I don't know, maybe you don't want to think about those, but I kind of sometimes like to think about those. And see where I land with a lot of those. So, do you think the brain is like a computer? Is that the metaphor to use?
It goes through a similar processes. Like it's mostly like reaction.
Yeah. You think it's somewhat similar?
Yeah.
After that.
Obviously not, like there isn't a brain like biologically, but like I would think like a lot of it's processes and patterns and like if you like fully program it, like with emotions, like I feel like it can make it like very similarly and maybe even better sometimes with some people who are maybe not as expressive or
Right.
that so.
Yeah.
I mean it's not the same thing, but
Yeah. It's similar, right? Okay. Well, I'm going to jump back. Let's get you going. I don't know. I always think every week I think, oh, this week's learning activity is going to be really hard, taking forever, even with AI. And then you do it with AI, and it's so much faster. So we'll see how this week goes. Okay, let's break into teams here. So let's do Jeffrey. We'll do that side of the room. Allie. And we're going to give you Taku, who's online. So you have to work with that. And then we'll do Addison, Grace, and Johnny. We'll do the left side of the room and the right side of the room here as our in-class teams. So find the learning activity and open it up here. I'm just going to walk through the beginning of it, show you what we're doing. So again, we're going to be programming kind of Turing machines, defining Turing machines. You're going to do three things. You're going to have, I think, 3 or 4 problems, and each one you're going to write a Turing machine program, and we're going to use this syntax. There's not necessarily a standard syntax for Turing machines, so we're going to use this syntax. And if you ask AI, you can give this syntax to AI. It will write the programs in this syntax too. So we're always going to give it the current state and the current symbol that we're reading off of the tape. And then we're going to have the little arrow, and then we're going to give it what's the new state and the new symbol that we're writing to the tape, and then the direction we're going to move that here on the tape. And then we're going to draw state transition diagrams here. And again, here you can use, I just use Google Draw for this. But you can just draw this out on paper. It might actually be faster. You can see, so basically each state is a circle there. We label some states as one state as a start state. We usually just draw a line with it, or label that as start, or somehow indicate that as start. So here I just wrote start, pointing to that. So that's where we start there. And then we can denote some states as like a halt state, or else an accept or a reject state. Sometimes we can just mark some states and say this, if we end up in this state, it's an accept state. If we end up in that state, it's a reject state. That's fine too. You can maybe put them in a different, like sometimes people double circle them, or put them in a different color, just write accept on them or something like that. Again, there's not necessarily standard stuff. Now, with our transitions, we're going to say what we're going to read. So here we're saying we're reading a 0, and then we do a slash, and then if we read a 0, we write a 1 and we move to the right for this. So we specify all of our rules in our transitions here. So if we read a blank, we're just going to go to halt. And again, we really don't care what we write or what we read at that point here. But actually, we're reading a blank, we're writing a blank, and we're just staying right there, actually. So you have to draw state transition diagrams here. And then we're going to use this Turing machine simulator from Vassar here, like this. So let's just look at it. This Q0 is the initial one. So again, we're gonna go through a binary number and then swap all the bits of it. So in the Turing machine simulator, I'm just gonna type in a binary number. It doesn't really matter what it is. Okay, and then we're gonna go through and it should flip all the bits. So if it's 0, we'll flip it to 1. So again, we can add some rules here. And I'm just gonna make one current state and call it Q0. Where if we read a 0, we're going to write a 1, and we're going to move to the right, and we're going to stay in state Q0. And we add another rule. If we read if we're in Q0, we read 1, we're going to write a 0 and move to the right, and we're still in state 0. And again, that's what this diagram says. So if we read a 0, we write 1, and to the tape, we move to the right, and then again, this arrow says we go back to state 0, Q0, and same with the other one. So those are the two ones here. I'm going to add one more. I think this would actually be enough. We just get to the end and there won't be no more rules. I'm going to add one more rule for halting. So I'm going to say Q halt. I'm going to say if we're in Q0, and I'm going to just say if we read a space here, so I'm going to use the number sign as kind of that, and we write a number sign, move to the right, and then we're in Q halt. I think number sign matches any character, any rule that's any like an empty space, I think, in this simulator. So now, once I get that in place, I can I don't want to just run it. I want to step through it. So I'm going to read. It should read that, oops, I have to change my state. So my state is going to be Q0. So you can type in your starting state here, Q0. Again, you can label your states anything you want. I tend to use Q in the number, but you can call them anything you want. So we're going to start there. It's going to read that 0. Now to read this 1 and change it to 0. It'll go through each one step by step. And then at the end, it'll be in halting state and no rules will match. So then that's what you're trying to kind of do. You're going to write out your code here. You're going to draw a diagram of it. And I actually don't need this blank going to Q halt necessarily. And then we're going to write this in the simulator for this. So, but again, we want you to do this here. So you're going to do even parity bit. You're going to do binary increment, accepts A to the n, B to the n. So a fixed number of A's and the same number of B's. And then binary palindrome recognizer. Oh, and unary subtraction. See if you can do those stuff. So again, I don't know how you want to do it. You can decide if you want to have different people do different parts of this and do, someone do the whole thing here, or if you want someone to do the state transition diagram, someone else to do the simulation. I've covered them different ways, but I don't care how you do these. Just do them. Okay? Questions on that? Okay, and just you have to communicate with talking somehow.